Let's continue the discussion of discounting, turning the attention to hyperbolic discounting. This is where we ended. I argued that discounting should reflect the will of the people without ignoring the far future, and discounting should be consistently applied across domains of public policy. And then I argued that this cannot be done with exponential discounting. So that raises the question, are there alternative forms of discounting that might do the trick? In order to understand the first such alternative, we need to look a little bit closer at these properties of exponential discounting. So a discount rate, or rather a discount factor, is the price of time. It measures the value of something that happens in the future relative to today. Or for that matter, it measures the value of something that happens at a particular time relative to something that happens at another particular time. And the relative price, according to the discount factor, is given here. So the value of something that happens in year t plus delta is this. This is the discount factor for the year t plus delta, and that can be expressed relative to the year t. And then if you work through this equation, what you find is that this only depends on the time that has passed between the 2 years, but does not depend on when it actually happens. It only depends on the distance between the 2 years. Now this is a very handy property because this implies time consistency. So if you take again the relative value of something that happens in year S versus something that happens in year t, and then we let delta years pass, then we have the relative value of S plus delta and T plus delta, and then the delta simply drops out of the equation, and we have the same relative values. Now this is true if we use continuous time. This is also true if we use discrete time. You can work through these equations and you see again that the delta drops out of the equation. Now this is known as time consistency. Essentially, this means that if you make a trade-off between a return in 10 years time and an outlay today, so an investment now that pays off in 10 years time, you calculate the net present value, you make a decision, is this a good idea, yes or no. Then if you wait a year and you make a decision between an outlay, a capital investment a year from now, and then a return 11 years from now, that's the delta that you see here, then you should not reach a different decision, provided that prices haven't changed, technologies haven't changed, institutions haven't changed, information hasn't changed. If nothing has changed, then you should not revise your decision. The trade-off between an investment now and a payoff in 10 years time, or an investment tomorrow and a payoff in 10 years plus a day from now, that should not make a difference if you have learned nothing new during the day. That is the property of time consistency, and the exponential discount rate, the exponential discount factor, immediately satisfies that. As you can see, exponential discounting implies time consistency. You can also turn it around, and actually time consistency implies exponential discounting, because there is no other function that satisfies this particular property. So this is a good thing to have. This is a good theoretical property for a discount rate. But there's also a very peculiar implication of this. Here we have the relative distance between 2 years again, and what I showed is that that does not depend on the t, that only depends on the delta. It only depends on the time passed. It doesn't depend on when this decision is made. And this is counterintuitive. Essentially, this says that the relative difference, price of time between year 10 and year 11 is the same as the difference between year 100 and year 101, and between year 1000 and year 1001. And that is very strange, because we can tell the difference between now and next year, and we can tell the difference between next year and 2 years from now. But can we tell the difference between 10,000 years from now and 10,001 years from now? Exponential discounting says those two distances are the same, which is very counterintuitive. There is now also plenty of experimental and observational evidence that suggests that people do not discount the future like this at all. They do not use exponential discount rates. One way of solving this is to stick a log in, that instead of making the discount factor a function of t, we make it a function of log t. And then the relative distance between 2 years depends on the time horizon. If you work this through, you get to log 1 plus delta t, and then time shrinks, the delta becomes less important if we move further out in time. Actually, the difference between year 10 and year 11 is then the same as the difference between the year 100 and the year 110, and between the year 1000 and the year 1100. Now, the first to come up with first to come up with observational evidence about all this was Maureen Cropper, and the guy who came up with this particular expression is Jeff Heal. So this is one way of having essentially a discount rate that falls over time, that essentially the discount rate becomes smaller as we look further into the future. Which then implies that if you have a project with a long time horizon, like investment in greenhouse gas emission reduction, that justifies a lower discount rate than a project with a short time horizon, for instance, investments in road safety. And you can consistently apply different discount rates without contradicting yourself, without saying some things are more important than others. But automatically, if you use a procedure like this, then you do not discount the further future as hard as you would discount the nearer future. The problem with this particular alternative is that it's entirely ad hoc. So Maureen Cropper observed these things. People seem to have lower discount rates as they peer further into the future. And then Hill just said, well, we can do this by plugging in a log. It's entirely, the observations are not ad hoc, but the math here is entirely ad hoc, and that is not something that we like as economists. Now there's an alternative way of finding the same result. Or rather, there's two alternative ways. Let's look at the first. Let's assume that there are two people and that they disagree about what the discount rate should be. One says the discount rate should be 1% per year, and the other says the discount rate should be 7% per year. And let's look at the present value of a payoff of €1,000. And if €1,000 is paid in a year's time, then the guy who says that the discount rate should be 7% would value this at €935. And if the payoff is in 100 years time, then he would value this only at €1. And if the payoff is in 400 years time, then it's essentially worthless. The person who argues that a discount rate should be 1% has a different opinion. He would value the payoff of €1,000 in a year's time at 990, in 100 years time of 370, and in 400 years time she would still value it at 19 euros. So this just illustrates again the power of discounting. Now the two of them disagree and they need to somehow reach a joint decision. So one way of doing that is to split the difference, and to split the difference on the discount rate and use a 4% discount rate instead, which is the average of 1 and 7. And then this is the value of the payoffs. But splitting the difference on the discount rate is not the right thing to do. What matters for our net present welfare calculations is the discount factor rather than the discount rate. We multiply the payoff with e to the power minus rho t. Not with rho, no, e to the power minus rho t. So it makes more sense actually to split the difference on the discount factor rather than the discount rate. And that is what is going on in this column here, where you take the average of 990 and 934, which is 962. You take the average of 370 and 1, it's 185. You take the average of 18 and 0, that's 9. So this is your average discount factor. And then what you can do is calculate the equivalent discount rate, the discount rate that would get you to this particular discount factor. That's not 4, that's 0.391 in the first year. And it is not 4 after 100 years, but it's 0.17. And after 400 years, it's 1.2. Why is this? Well, this follows from Jensen's inequality. But the intuition here is that essentially we're averaging over preferences. C still cares about whether things happen 300 years from now or 400 years from now. C has an opinion about these things. He is indifferent. This guy is indifferent. This girl isn't. So if you're going to take the average between the two, one doesn't care, the other does care. Who are you going to listen to? You're going to listen to the person who still has an opinion about these things. And that implies that the further you peer into the future, the more important her opinion becomes relative to his opinion. And that is intuitively why the discount rate falls. As you peer further into the future, you use a lower discount rate. Now this is one interpretation or one derivation. There is an alternative derivation, and economists do not like to compare the utility of different people because we cannot look into people's head, and it makes it very difficult to compare utilities. You could also say we have one person who is undecided whether the discount rate should be 1% or 7%, and attaches a 50% probability to either. And that person would also not average the discount rate, but average the discount factor, and therefore come up with a certainty equivalent discount rate that falls over time. Right? And actually you can show that if we wait long enough, if we go take 400 to infinity, then in fact the discount rate would fall to the lowest discount rate in the sample. So that is the intuition. Now, this was derived by the two guys you see here. The disagreement argument was done by Christian Gollier. The uncertainty argument was done by Marty Weitzman. Weitzman also showed that if you actually make assumptions about the distribution of the uncertainty about the discount rate, particularly if you assume that that follows a gamma distribution, then you have a nice closed form for that declining discount rate that looks as follows. That discount rate at time t equals alpha over 1 plus beta t, where alpha is just the location parameter that just anchors things, but if there is uncertainty, if there is a spread of opinions or uncertainty about the discount rate, then the further you look into the future, the larger t becomes, the lower the discount rate becomes, right? So that may be exactly what you want. Essentially, this means that for short-term investments, you use a high discount rate. But if time horizons get longer, if you peer further into the future, then your discount rate becomes lower and lower and lower and lower, and that implies that you could effectively use a lower discount rate for long-term investments, as in climate change, versus short-term investments, say road safety or pensions. This matters quite a bit for the social cost of carbon. That is what you see here. These are results from one particular model. What you're looking at here is the constant discount rate, and then here we have a declining discount rate. And the way this is set up is that the discount rate starts in year 1. The discount rate is the same for the two, but here in this column, the discount rate falls, and in this column, the discount rate stays at its initial value. And it makes a big difference. If we follow Weitzman's scheme that I just showed you, then the social cost of carbon goes from $3 per ton of carbon to 107. That's quite a big difference. Here there is an alternative form of a declining discount rate. It actually doesn't fall continuously, but it falls stepwise. And then the social cost of carbon goes from 8 to 22, still quite a big difference. The reason that I put the Green Book discounting up here is that Weitzman is probably theoretically the more elegant way of doing it. Green Book discounting is the discount rate, the declining discount rate that is used by the UK government in evaluating public investments. And what you can see is that, yes, this is a way of increasing our care for the future in a way that seems consistent with economic theory. And if we increase our care for the distant future, we increase our care for climate change, and therefore we raise the tax that we would want to place on greenhouse gas emissions.